Hi everyone, this is Farhad Fallah from Allec Company. In this video, I'm going to show you how to run hardware-software co-simulation solution for Zinc-based SoC designs using Allec's Rivera Pro and Xilinx QEMU. Alright, let's go over the outline of this video. First, we're gonna start with some introduction about the heterogeneous devices. Then we talk about the requirements to run this solution. Then we talk about the limitations that we have, especially for the Linux system. Then we prepare the project files. We're gonna create the hardware project, and then we prepare the design for co-simulation. At the end, we run the co-simulation and we test it, and we talk about the known issues, and then we wrap it up. Heterogeneous SoC devices such as Xilinx Zinc include software and hardware sides. In the software section, we can have applications or Linux systems, and in the hardware side, we can have hardware IPs to communicate with different peripherals. It could be FMC daughter cards or any other peripherals on the board. So the combination of programmable logic and the processing unit makes it challenging for verification engineers to verify the entire design, because on one side we have an application running either bare metal or on a Linux system, and on the other side we have our RTL IPs. That's why it's called hardware software co-verification. Allec provides this solution using Xilinx QEMU and Rivera Pro Advanced RTL Simulator. In this solution that I'm going to show you how to run it in a bit, Xilinx QEMU is used to emulate ARM processor on the Zinc. And then Rivera Pro on the other side runs the simulation for the hardware side. The communication between the QEMU and Rivera Pro is done using the remote port IPC, and also we have the systemc library inside simulator, which is Rivera Pro here, to get the data, read the data from the IPs and communicate to the application side, which is inside QEMU. Alright, without further delay, let's go over the requirements that you need to run this solution. We need Rivera Pro version 2021.10 or any newer one. We need Xilinx Vivado 2021.1 and Xilinx Petalinux 2021.1. There are also some limitations in setting up the environment. So Windows is not supported. These are the supported platforms that you see and their version, and this example is verified with operating systems CentOS 7.x, it could be anything, and Ubuntu 20.04. So first step, we need to create the hardware project. To do that, we need to first add the Tyson 1 or any other Tyson board files into Vivado. In this version, the newer version of Vivado, which is 2021.1, we need to use this command to add the board files. In previous versions, we could just copy and paste the board files folder into the data/boards inside Vivado installation path. I'll show you in Vivado how to do that, and then we create a project for Tyson 1 board or any other board that you are using. There are some steps inside AppNote that you can follow to create this design right here, and then at the end you need to have a block design looking like this. Okay, now I'm on my Linux machine and I've opened Vivado 2021.1, and the first step was to add the Vivado board files to Vivado using that command. So I'm writing this command here. And then the path to the Vivado board files on my system. So I've already downloaded the Tyson GitHub files. I'm going to Tyson 1 board, Vivado board files, and then this is the folder that I'm going to use. To get this address, I just type pwd. So this is the path. I copy the path and add it here. Then I'm just double checking everything is correct. Set param board repo path. Okay, hit enter. So the board files are right now added to Vivado. So in the next step, I need to create a project. Go to File, Project, New, and next, call it Project 1. RTL project. At the moment we don't have any source files, no constraint. Here I go to boards and then I choose Tyson 1 board, which is the first one. Next, and finish. So the project is open. I create a block design. I call it design 1. Here I can add IPs, so I add Zinc processing system. So I can run block automation. Make sure that you apply board presets. Click OK. Now that processing system is set up, we need to communicate with user LEDs and user switches on the board. There are two ways to do that. The first one, you can go to the board and then go over PL user LEDs and PL user switches, and you can connect them to the board component. The second method is to just add AXI GPIO here. So the GPIO 0, based on the app node, needs to be connected to user switches. So I go over here, instead of custom, I choose user switches, and then run connection automation, check all of this. So now this GPIO is connected to the user switches. I need another GPIO to be connected to user LEDs. Open this, change this to connect to user LEDs. Run connection automation. So we have the second one also connected to the user LEDs, and the first GPIO is connected to user switches. So we need to check the address for each GPIO unit. You can see GPIO 0 is connected to 0x41200000, and then LEDs are connected to 41210000. So now I need to save the project, and then let's validate the design. Okay, now I need to create the wrapper. Go to sources, right click, create HT wrapper. Let Vivado manage wrapper and auto update. Okay, now we have the wrapper created. Next step is to run the bitstream generation, which is gonna take a little bit of time. Okay, you can generate bitstream. So it's gonna go to the default launch directory. Okay. Alright, the bitstream is generated. Now I need to export the hardware. I go to File, Export, Export Hardware. Next. Make sure to check the include bitstream. Next. This is the location, goes under project 1. The file name is called design1 wrapper. Next. And finish. Gonna take a little bit of time. Now that the .xsa file is ready, I go to the project folder to check if it's there. Project 1. I see the file right here, so I can replace it as it explained on app note with the one which we provide in the pre-built design on GitHub. So if I go to the Tyson QEMU folder, there's example hardware here. So you can just replace your hardware, whatever IPs you have in there, doesn't matter, with this one, and then make change to the simulator file, run the simulation. So we created the hardware project inside Vivado, and the next step we need to prepare the design for co-simulation. First we need to update the config file and make sure that the correct path is used for the tools that we are using, which is Rivera Pro, Petalinux, and Vivado. And then we run this config file. We generate the sources by running .prepare underline files. This might take around 30 minutes because it needs to create a Petalinux project. And then we see this type of sample result on the terminal. Alright, so the Vivado project. So you can either use the Tyson QEMU folder that you downloaded from GitHub, and then you just run the script. Here we have the config.sh and then prepare underline file.sh. Or you can, if you have a different design example, it's a custom design, you can just replace it with this .xsa here and then run the design. So here I've already replaced that. Going to the folder, just open the config file. I need to update this to get the right path to each software. So first for Rivera Pro, this is the path that I have. Copy this path. Paste it here. And for Petalinux, so as it's mentioned also in the app note, make sure that you install Petalinux under the home directory of a non-root user. So I'm not root on this system, so it's going to be under my root directory. This is the path that I have for my PetaLinux. To make sure that it's under the tool folder. Copy and paste it here. Then Vivado. Here's the path. So it might be different on your system. This is the path that I have. So I'm going to save this file. Alright, let's run this config file. I'll close this. Alright, now I'm going to run the other command, which is right here, to prepare the files. I'll run this prepare underline files. So as I said, it's going to take around 20 to 30 minutes depending on your system. So I'm going to pause this video and come back again. Alright, now the files are ready. And then we need to run the code simulation. To do that, I just run code simulation. I'm going to get two windows, one for the QEMU. That looks like a Linux terminal. And the other one is Rivero Pro. So this is gonna take a little bit of time for all the files to be prepared. So I'll pause the video and then I'll come back again. Alright, now the code simulation files are prepared and I have a window for QEMU and then the Rivero Pro window right here. So as it is explained on the app node, I can use devmem command to write into an address. So I'm using the address to LEDs. And then I write 0x55. So if I can either refresh simulator or I can stop it and then run it again. So here I see I give it a little bit of time for it to go through. If I stop it, so I can see 55 is written into LEDs. So the value of the LEDs is 55 right now. To run any new command inside QEMU, just make sure that the Rivero Pro is running, the simulation is running, so you are able to right here. For example, I'm going to read what's inside that address that we just wrote in it. I type 4121.0.0.0 and here. So it shows me that 55 is there. So if I just write there again or another number, so I try to use 0x, the same address for LEDs. I try to type, I write 44. So inside the simulator, I'm going to stop the simulation so I can see that 44 is now written. Before it was 55, now we have 44. Okay, because I didn't give it too much time, that's why it was a little bit weird to get to this point. So 44 is now written into LEDs. There are some issues that you might face while running this. There's an example. For example, you're gonna see a long delay when the QEMU terminal reaches to this command. And if you want to close the project, just make sure that you first close the Revero Pro, then you close the QEMU terminal to avoid any error. And then you might need to maximize the value of this variable right here inside your Linux to pass some errors that you're gonna see while running this design example. You can use this command here to change that variable value. Alright, this brings us to the end of this video. You can download the app note from our website, and then just shoot us an email if you have any questions. We are here always to help you. Thank you for watching this video.